Okay, so today we're very fortunate to have Chad Scherrer, who is an expert on probabilistic programming and a prolific developer of such libraries, tell us about applied measure theory for composable statistical modeling. So please, Chad, take it away.
Thank you, Evan. I'm happy to be here. My name is Chad Scherrer, and I'm founder of Informative Prior, where we do research and development for statistical modeling, probabilistic programming, that sort of thing. I'm going to talk about applied measure theory for composable statistical modeling. So let's jump right into it, talk about the goals for this talk. So I want to introduce measure theory at a pretty high level. So some of the very technical details that don't contribute to kind of our main goal, we're going to sweep some things under the rug, though I'll try to mention them at least very briefly as we go past them. The focus is going to be really on building structural intuition and seeing the kind of composability that we can have in a system like this. And so we'll introduce some basic concepts in measure theory. And as we introduce them, we'll see these implemented in MeasureTheory.jl and Tilde.jl. So kind of hop back and forth between kind of the foundations of the theory and what the implementation looks like. Okay, so let's motivate. The big question I hear from a lot of people when we start talking about measures is, why do things in terms of measures at all? Why not stick with distributions? Everybody's comfortable with distributions. There are packages for working with distributions all over the place. So why do this? Well, if we look at a standard normal, we talk about the probability density function, and it looks something like this. If you think about density in other contexts, you might have a mass density of some solid object. You might have a population density, and all of these are relative to something, right? A mass density is relative to a volume. A population density is relative to some area. So what is this density relative to? Well, if you think about how this density is really defined, we have some small d lambda, and for that d lambda, we have a small probability dp. So the density that we really have is dp over d lambda. And this is kind of a problem from a composability standpoint, because a thing we like to have is when we define a new object, we like for it to be defined in terms of other objects that are already in our space. So we have this kind of composability, and then we can build up lots of arbitrarily complex structures based on some simple primitives. But here already, for the simple case of a standard normal distribution, we're out of that, right? So it kind of hints at this idea that maybe measures are really more fundamental, and in some way it's more natural to work with measures all the way through. And because if we do this, there are a lot of things that we otherwise wouldn't even be able to express that are pretty easy to deal with when we just use measures directly. Okay, so our approach is, for constructing these things, we're going to have a few primitive measures. Primitive, I mean measures that are not expressed in terms of other measures. So we have one called Lebesgue measure and one called counting measure. And then we have lots of combinators for building up new measures based on existing ones. And in terms of computation, each measure is going to have a log density def function, and think of the def there as this is how this measure is defined. And then it also has a base measure. So if we think about a graph taking a given measure to its defined base measure, this forms a tree. If you take a base measure of a base measure of a base measure of a base measure, eventually you'll reach a fixed point. And then in practice, we have several of these trees, and we connect some of these using another 3-argument form of this log density def. And that allows us to compute relative densities between lots of different measures. So now we're going to talk about some fundamentals. We have just a couple of these before we get into seeing some of the implementation. So pretty fundamental to measure theory, at least in a theoretical sense, is this idea of sigma additivity. So the idea is if we have some function that takes a set of sets as its domain, so for a given set, it returns a non-negative real number. That's sigma. Oh, and by the way, can you see my cursor when I move around on here? Okay, good. It's like talking with my hands. Okay, so it's sigma additive if I have a disjoint union of these EK sets and I want to apply that function to them, I just sum these things. So it's a pretty simple definition. Really, the most complicated thing about it is that this is a countably infinite set, but it's kind of what you would expect in terms of additivity. So given that as our kind of most core fundamental, a measure then is really just a sigma additive function. So it has as its domain some specific subset of a set X. So if it's set X, we have some sigma, which is a set of sets of X, and mu takes one of those sets and assigns it to a non-negative value that we're going to call the measure of that set. Okay, so sigma here is the set of measurable sets, and mu is a measure on X. So X is the underlying space for the measure. And to simplify this, we'll write mu in M of X, for mu is a measure on X. Now, there are some other things that usually come into play here. People talk about sigma algebras, and when you're building this from in a mathematical setting, that's really important. Our library doesn't explicitly address sigma algebras. We consider sigma algebras to be implicit to a given measure. Okay, so we're not going to go into details of that. And I think if we just treat this as there is some sigma for which this is a function, that is enough to make everything work for our purposes. Okay, and as we go through this in a couple of places, we'll talk about tilde. So I'm going to address that bring that up very early. And that's just because it gives a very nice way, a very simple way really to write these kind of compositions of measures. So probably some people here have seen probabilistic programming. Tilde is maybe a little bit different than some systems. Here we treat this as a model. If I say at model S, begin, and then I'm going to draw X from a normal with a standard deviation of S, and then I'm going to turn X squared. So think of a tilde model as a function that has some random choices, or more specifically, or more generally, choices from some measures. And when we write a measure in this system, what we really get is a measure over the latent space. Okay, so if we call rand on, say, M of 3, then we get this named tuple. And if we want to evaluate the log density of one of these things, we have to also give it a named tuple. So both of those ignore this return, the rand and the log density of both ignore the return and work entirely in terms of the latent space. If we want to bring the latent space, if we want to bring this return value into play, then we use the predict function. So if I say predict M of 3, that runs the model, making the random choices along the way, and I get 9.8 in this case. I can also give it any subset of the latent space. So here, if I give it a value for X, now the process of prediction is deterministic. And so if I pass in a 2, I just get a 4. Okay, so let's talk about measurable functions. So we talked about a measure is a function, but measurable functions are very different. Measurable function is just, instead of being from a set of sets to the reals, it's between any two domains. We think of these as just being sort of, this might be R2 and R or something like that. So nothing too fancy. So the analogy I like to make here is in terms of continuity. So when you talk about a continuous function, you look at its inverse image of an open set, and the condition for a function to be continuous is that that inverse has to also be open. So for a measurable function, the same thing is true. if we start with a measurable function, if we start with a measurable set in Y, we take its inverse image. Now we get, as a result, a measurable subset of X. Okay, so we should note that, so let's see, yeah, here's the way to write this mathematically. My cursor is messing up, there we go. Okay, so if we have a measurable subset of Y and we apply the inverse image, then we get a measurable subset of X. So I should point out that this assumes that these measurable sets are known a priori. And again, in terms of the implementation, this is not something that we have encoded which sets are measurable. This is just taken as implicit as part of a given measure. Okay. A lot of what we do is in terms of kernels. So we should talk a little bit about kernels. So a kernel is a function from a pair of an X and a set of sets, and it gives you a non-negative value. And there are some additional constraints on this. It has some measurability constraints. If you fix either one of these, then the result either has to be a measure or a measurable function. But for our purposes, it I think simplifies things a lot. If you look at a curried version, so if you curry this and treat this as a function only of the first value, if I give it an X, the result is a function from sigma Y to R0 plus. And that function is itself a measure. So we can treat this whole thing as a function from X to measures over Y. And we can also write for this, kappa is in KXY. So this already for the category theory crowd is probably hinting at that there's a category here. In fact, this is a category. This is the category of Kleisli arrows. So it turns out that M is a monad and KXY is a category of the Kleisli arrows. By the way, we talk about kernels, but this is another nice thing about using K, is that K is kernel or Kleisli, read either way. Also, I want to point out that in statistics, people talk a lot about distributional families or parameterized measures. So if I just say normal without a mu or a sigma, maybe one of them is fixed or maybe the other one is unknown, this itself is a kernel, right? Because if I say normal with unknown mu and unknown sigma, then if you give me a mu and sigma, I can give you a measure. Okay, so it takes values and turns them into measures. So parameterized measures are themselves a kind of kernel. Now, in measure theory, we can look at this pretty directly. If I say K equals kernel do lambda, and the thing it returns is a normal with a mean of lambda and a variance of lambda. I can write this for a normal approximation to a Poisson. Then I can apply this just like a normal function. And oh, by the way, this is Julia's do notation. So I could instead have written this as kernel of lambda arrow normal mu equals lambda sigma squared equals lambda. This is just a kind of syntactic nicety that Julia allows. So this looks like it's not very different than a function, but there are a couple of things going on here. As opposed to a generic function, making it into a kernel lets it know that the return value is a measure. Excuse me. There are also different kinds of kernels. So when I call this, I might get a generic kernel, or I might get a typed transition kernel, or I might get a parameterized transition kernel. So a typed transition kernel is one that knows, oh, by the way, this also returns, I know that it returns a normal even without knowing what the argument is. And a parameterized transition kernel knows that it's a normal, and it also knows the specific parameterization. Okay, so there's kind of different degrees of how much the kernel object might know. And we don't know a priori which of these we'll get. This depends on the compiler. So we've set this up so that the semantics are identical, whichever of these you get. It just will be a difference in performance. So if you end up with a parameterized transition kernel, that's obviously the best possible case. We want that to be as stable as possible. It does rely on the Julia compiler itself. So it's difficult to pin it down entirely because that's not something that is included in the specification of Julia. But also users can take steps like making types more concrete tends to help this. So if I would say do lambda : float 64, then that probably helps the compiler out a little bit. And it says, oh, I know that you're going to give me a float 64, so then I can infer a little bit more concretely what the result will be. So I mentioned that parameterized measures are kernels. So here are some examples of, well, these are parameterized measures that have been instantiated, that have been given arguments. So I could say M1 equals normal 2, 3. By default, if you just give it 2 values, we try to make this align with distributions.jl. So this says the mean is 2 and the standard deviation is 3. Now I can call its log density on some value and I get a result. But equivalently, I could say mu equals 2 and sigma squared equals 9. Or I could say lambda equals 1/3. We use lambda as the inverse of the standard deviation. Like inverse scaling, so lambda is the inverse scale. Sometimes people use the term rate. And if you look at a lot of distributions, the rate is very often called lambda, so we kind of standardized around that. And then the precision tau is, so from the standard deviation to the variance, you square it. From the rate to the precision, you also square it. So this is just 4 different parameterizations of a normal parameterized measure that come up, and just kind of showing that you get the same result in all cases. Okay. Integration and densities. So integration is a way to start with some measure and get another measure. So the first example that we saw, we started with the measure on the real line. That's turns out Lebesgue measure, just the length. And we put a density over that. And as a result, we got the normal distribution. So we can do exactly that. So we can have some function. So given a measure over x and a function from x to the non-negative reals, we can say d nu equals f d mu, and then we can integrate that in this way, and that gives us a new measure over the same space. Going the other direction, we can take the density or the rate on nicotine derivative, and it's just kind of what it looks like. So you have there's a fundamental theorem of calculus that you can work with here. Let's look what this looks like in terms of MeasureTheory.jl. I can take a normal, and this integral exp is that's not 2 separate things. That's one single token, integral exp of normal, and then here's this Julia's syntax again for functions: do z 2z plus 1. So my density is going to be z goes to 2z plus 1. And I'm applying that density on top of, I'm integrating that on top of a normal measure. So if I do that, I get this density measure object. And if I plot that density, I get, it turns out to be the right thing. So you integrate, you put a linear function on top of a normal, you get another normal. And we can also go the other way. We can say this script D is for density. So I have the density of 2 measures. I take the density, and if I plot that on a log scale, then I get the 2x plus 1 that I started with. Okay, so this is very kind of fundamental theorem of calculus. This density used to be very simple. We made it. We've kind of refactored this a couple of times, and I think we might go back to a simpler version because this ought to be just a simple function. So that's still potentially changing. And we have likelihoods. So likelihoods are used all over the place in statistics, and the idea is if you have a kernel and you have an observation in the target of that kernel, but you don't yet know what the parameters are. So this is why likelihoods come up all over the place, because that's exactly what we have in statistics. So if I have a kernel kappa, this likelihood is, well, what happens to any given theta? So if I have a theta, I'm going to apply my kernel to that value and then look at its density with respect to some base measure. Now that gives me a function. Let's see, so kappa of theta gives us a measure over y, and then taking the density of that with respect to beta gives us a function on y, and if I apply that to y, then I get a real number. Okay, and here's how these look in measure theory. So maybe I have 10 replications of a normal, but I don't know what the standard deviation is. So let's say we have a prior of a half normal, so that's this blue line. And then I have a likelihood. This is that same syntax, that same Julius do syntax again. So my kernel, the function I use to build my kernel is sigma goes to a normal with sigma equal to that sigma to the 10th power. So that's just a power measure, which means it's a product measure of 10 independent copies of that measure. And I'm applying it to some observation. So here I started with some obs that is 10 real numbers. So now I have a prior and a likelihood. And I can use, so if I look at the likelihood by itself, that's this kind of gold curve. And in order to get the posterior density, which is what we use for Bayesian inference, I take the prior and really in terms of, for given one of these values, I just look, what is the prior, what is the likelihood, and then I take a product. So our combinator for that is this O dot, which is a pointwise product. So we just say post equals prior O dot like, and then we get this green curve for the posterior density. Push forward measures. So if we have some measure and we have a function that starts with that underlying space and maps to some different y, we should be able to get a measure on y as a result. So a way we can define that, the way we can define that to make things work, I am stuck between my screens here. There we go. So the question is, what is the measure of some subset of y? So if I have some measurable subset of y, call it b, I can take f inverse of b, and that gives me a subset of x. And then I can take mu of that subset. This is just the definition of push forward. Now, in some cases, push forward is very straightforward, no pun intended. For sampling, it's easy, right? Because for sampling, I could say, well, if I can sample from this mu, then I take my value and I just send that value through the function. That's very simple. But what about if we want to evaluate the log density, or just evaluate the density? For that, in some cases, we can do it without f being invertible. But typically, to make it sort of always work, we really need f to be invertible. And in that case, all kinds of things, nice things happen, and the things simplify quite a bit. So this is another combinator, so let's give it a name. So the push forward we'll call f star. So we defined a measure nu to be f star of mu, and that is in m of y. Okay, so let's see what that looks like in Tilde. So for all of these, we'll reset our random seed, and we have some f of x. In this case, it's just 3x plus 4, and we'll start with a normal measure. We can say, let's first find that push forward, and then let's draw a sample from it. Or we can sample from the underlying measure, and then just push that, evaluate the function on that point. And so if we put both of these into tilde, we have this push forward combinator is in measure theory. So we can say push forward of some function and some measure. And of course, we could still turn things around and use the do notation as we did before, if we like. And then y is drawn from new, and we're going to turn y. And then in order to get the return value and not the latent space, we need to say predict. So we're going to predict using our random number generator, m. We get this value. If we instead do kind of without using the combinator, we can draw it this way, and then we get exactly the same value. So these might seem to be exactly the same, and they are in terms of sampling. But if we were to do inference on these, there are some differences. And typically, this y is what we would call, statistically, we call this a non-centered parameterization. So there can be significant differences in doing Bayesian inference on one form versus the other. So it's important to have both of them available. Okay, this m that we mentioned back at the beginning, this is a functor. So for something to be a functor, we need to know what happens, what does it do to points, and what does it do to functions. So on a given point, it turns out in this case, it's the Dirac measure on that point. And for a given function, it takes a function to its push forward. So the function is on points. The push forward is a function on measures from one measure to the other. And this is a functor from morphisms on points to morphisms on measures. And it's also a monad. So we maybe hinted at this a little bit at the beginning. You kind of need it to be a monad in order for the tilde syntax to make sense, right? Because you need to be able to say, draw something from some measure and then feed that into the next value. And in terms of functional programming, that's almost always in terms of a monad. So how do we do this? Well, the unit or the return of m, this should just be m. The unit or the return is delta x, just the Dirac measure again. I should say, in case anyone doesn't know what Dirac measure is, this is a measure where all of the mass is on a single point. It's Dirac measure. Okay, what about the bind? So for a monad, we need a unit or a return, and we also need a bind. So bind says, given some measure and some kernel going from x to measures of y, we need to return this operation that gives us a measure in y. Okay, and this is the usual symbol you see in functional programming. I'm not sure from a category theory perspective what, maybe there's a different way of writing this from category theoretically. But the idea is we take kappa of x, we're going to integrate that over mu. So in terms of sampling, this is just draw something from x, use that value to draw something from y, and then forget the x value. So this integration is, in statistics, we talk about this as marginalization, right? So we're marginalizing over this measure and returning just one component. A nice thing when we're doing this in terms of Monte Carlo is marginalization turns out to be just throw that variable away. So that works out very easy in sampling. For densities, that's usually intractable. But this bind operation is really important, right? And densities are really important. We always need to be able to do those. So this is exactly why tilde keeps the latent space instead of trying to explicitly marginalize, because you can't always do it. And in fact, in most cases, you can't do it.
Can I ask a question about syntax here?
Yeah.
That last equation, x is a very little x is a variable, presumably ranging over capital X, because that's where d mu and kappa make sense.
Mhm.
And it would seem to me that in the integration, then b would be a subset of capital X. But that seems to be wrong, because b is supposed to be a measurable subset of y, the left side of the equation,
Oh.
a measure on y. So I'm confused. Can you unconfuse me?
well, let's see. No, you're absolutely right. So this should be. Okay, let me see. Yeah. So the thing we want to integrate over. Yeah, there's something messed up here. So in terms of the integration, we want to integrate over the X. It should be in the X space. So I think what we should do, I think we need to pull that back through kappa. Yeah, there's a subtlety here. I think what we need to do in this case is pull this, instead of integrate over B, integrate over kappa inverse of B. But I'm hesitating because that I might be missing a subtlety there. Let's yeah, I want to fix this, but I'm not sure that I can fix it on the spot. Is there a way for me to follow up after the talk?
So Maurice has a suggestion in the chat that
Yeah,
might be all right. Maybe you should check that out.
I did not see the chat. Let me see.
Oh yeah, we can also move on if you prefer.
Okay.
Pointing that out.
Okay. Yeah, let's there's like 4 more slides. And then let me look at the chat. But I'll need to like find where the chat is, and maybe we can address that. Okay, yeah. So that's definitely a mistake. So let's fix that after. Thank you. Okay, so that's in terms of the foundation, that's it. Now I want to talk a little bit about the implementation. So how do we implement? We have some measure, say normal 3, 4, and we want to take the log density of that on some point, say 1. What does that actually look like? Well, the simplest thing we could do would be just to say, just give me the log density with respect to its base measure. But base measure is, it's kind of an internal thing, right? Because you could define the same measure in lots of different ways. You could sort of have your choice of base measure. So the base measure is really chosen as an internal thing for computational efficiency. And when you're evaluating the log density, what we typically want to do to be consistent with other packages that don't work in terms of measures, at least explicitly. I mean, all of them are really using measures. But typically when somebody says, give me the log density of a normal, what they mean is with respect to the Lebesgue measure. And so we need a way to say, for any measure, give me something that kind of, a way to measure the log density that makes sense without referring to a base space. So what we do is we say, let's take the base measure of the base measure of the base measure of the base measure. Eventually you get to some fixed point. And we can take the log density at each of those steps. And then and then add these. So eventually, so basically what we're doing is we're taking the log density of normal with respect to this fixed point. So in this case, that's Lebesgue measure. And the way you compute that is you start with the measure itself, and then you take its base measure, get the log density, take its base measure, get the log density. You add all of these up as you go. Okay, so this shows each of those steps. In this case, normal 3,4 has what we call a proxy. So when a user says normal 3,4, it would be confusing if normal 3,4 returned affine push forward, blah, blah, blah of normal. So this affine push forward is what's really going on. But when the user calls normal 3,4, it returns exactly that. And then under the hood, it turns it into its proxy and then goes from there. Okay, so we have each of these evaluation steps until we get to the fixed point, and we add these up along the way. Now, the obvious concern that I would have seeing this approach is about performance. So let's look at performance. So this call made with the mu, sigma, and the x all chosen randomly. The measure theory does that in almost 7.3 nanoseconds. Distributions.jl is around 9.5 nanoseconds. And now that's it's tempting to claim like, oh, we're faster than distributions, and in some cases we are. In this case, I think that's a little bit strong of a claim, just because the error is we're pretty close to the error there, but it's certainly competitive. So and we do this through some tricks using generated functions in that evaluation. Okay, so we try to set things up to play very nice with the compiler. So you get the benefits of this abstract and very composable representation without having to pay any performance penalty. And in a lot of cases, you actually get performance advantages out of this. Okay, and that's my talk. Thank you very much.
Thanks, Chad. That was great. So we've got plenty of time for questions. So if anyone wants to start by asking a question, you can raise your hand, use it through the Zoom interface.
And how do I see the chat? Maybe yeah, I just need to stop sharing. Should I stop sharing?
You can. I mean, people may want to refer to your slides too. So okay, whatever you want to do. Yeah, the chat should be, if you go to the bottom of the screen, you should see.
I found it.
Okay. Yeah.
Okay. And meanwhile, it seems to have a good answer. At least the answer looks good to me. Type checks and everything. So, more than type checks. It makes intuitive sense.
Okay.
So I'll ask a question.
Yes.
Right. So in this talk, which is very interesting, you sort of described how different primitive, operations that you might want to do in probability and statistics, like such as having kernels and push forwards and so on, like how you can construct a library that lets you compose those pieces together. You didn't talk so much about like building a probabilistic, putting those pieces together to build probabilistic programming environment where you could do inference in a model. So I was wondering if you just say a bit about does this way of setting things up help you do that? Because I assume that's sort of ultimately where you want to go. Is that right? Or
absolutely, yeah.
Yeah.
So that's a great question. And in Tilde, a Tilde model, by the way, is itself a kernel. So, and it literally inherits from that kernel interface from MeasureBase. And so when you instantiate it, the thing you get is when you give it arguments, you get a measure. But in terms of inference, the way we do things is in terms of inference primitives. So there's this concept of running the model. So you could say, well, a model looks like a program, and it's kind of obvious how that program would be run, except for those tilde statements, right? So when you run a model, you run it just like you would run any program, but you need, in addition, some way to interpret when I see x tilde normal, what do I do with that? And so we have a collection of these different primitives. One of them is draw randomly from the right-hand side. One of them is evaluate the log density and increment some value and carry that through the model. There are a couple of different ones. And yeah, it's funny because certainly that's the end goal. Really a thing that I found to be more of a sticking point was this kind of some of these fundamental questions, and like, how do we even express these things, and how do we get these things to compose in the right way? In Julia in particular, for efficiency, what you really want in a lot of cases is to have very small steps between different representations. So you have some representation of an object, and you have some way to simplify it. But if you, instead of just jumping all the way to that end result, which might not always be the optimal way to represent it, you want to make very small improvements and chain those together, because you can write more abstractly ways to optimize some of those small improvements, and then it will sort of catch them automatically. And that, I think, has been a really nice thing about implementing this in Julia, is that you get that kind of help for free, and it works very nicely with the composability. But I don't know if that answered your question about.
Yeah, it partially does. Maybe I'll ask a follow-up. So, like,
Yeah,
I know you've worked on a package sauce.jl, which is for probabilistic programming, and you're now also working on Tilde.jl. And so I was wondering, in the move from the first to the second one, how does the work you described here fit in? Was it an attempt to address specific issues that you encountered in the development of sauce, or
right? Yeah, great. So yes, sauce, you can nest sauce models. It does have some composability, but in some ways it never felt very natural to me. So in part, Tilde is trying to make things feel more natural. Also, sauce works in terms of a DAG. So a sauce model has to be a collection of top-level statements. There can't be any for loops or things like that in sauce. And there can't be any mutation. I mean, it's pretty restricted. In exchange for that restriction, you get some advantages. But I wanted to explore doing something a little bit more, I guess, Julian, where we sort of allow a little bit closer to kind of arbitrary Julia code. And so that's a lot of the idea in Tilde is that just using the Julia compiler more, as opposed to only rewriting our source code and going through there.
Cool, thanks. That's very helpful. Are there any other questions from the audience?
Could I drag in a possibly tangential subject? Not that it's possibly tangential and possibly relevant. It's the other way. It might be tangential. It might be completely off topic. But does this relate to entropy of probability distributions? in a useful way, for example, to help understand what is really going on behind the scenes in entropy?
I think can in some ways. I've implemented entropy in SOS. It's an approximation. It's kind of a particle-based approximation to the entropy. I think there are some things we can do kind of from a more fundamental perspective, but there's not an obvious roadmap to me that, I guess what I mean is, I think there's a way we can do that, but there's nothing that we've done so far that makes that next step kind of obvious in terms of the way to address it.
Okay, thank you.
Mm-hmm.
Any other questions? Okay, in that case, thanks again, Chad. Really nice talk. And at this point, like, we can stop the recording and the live stream.